it's quite new for me, and I'm hoping we get back to normal. So anyway, thanks for coming, whether you're here in the room and also all of you online. I hope you can hear me okay online. We're monitoring that as well. So, alrighty. So I'm going to spend a lot of time talking on data visualization today, and particularly on doing inference for data plots. And it is in that area of exploring data and providing tools for us to be able to provide significance in relation to data plots. So the main reasons for this is that making effective data plots goes a long way to understand any problem, and it's a very, very important activity. I don't think we do it enough generally, but one of the biggest complications that's been there for many years, for decades and decades and decades, is that we have lacked the inferential machinery to do formal statistics with data plots. And my argument today is that not anymore. We've got the equipment to be able to provide statistical significance. So I'm going to start with sharing some of the stories of what I've learned from purely making plots of data. And I think I've learned more things about this world from making plots of data than from any other technique, than any other statistics that I've used. So here's the first example. I've only got 5. I have really hundreds and hundreds of examples that I could share, but I'm picking 5 to show you today. The first is, this is data from the OECD PISA, Program for International Student Assessment. And these are standardized test scores for 15-year-olds across the globe, at least in OECD countries. So most of the globe, but not all of the globe. I've picked a handful of countries just to make the plots more visible here. And we have math scores, reading scores, and science scores. And what's plotted is the difference between the average boys score and girls score. And so there's a 0 in the middle of each of the plots. On the right-hand side, are countries where girls scored better than boys on average. And in the left-hand side are where boys scored better than girls on average. The yellow line marks Australia on each of those plots. And so the first one here is math, and you'll see that there's a handful of countries where girls score better than boys on math on average. Qatar, Indonesia, Israel, Malaysia, and Finland are in that list. There's a lot of countries where there's no difference between the scores. You won't see this very easily, but there's a little bootstrap confidence interval around the average, the differences. And so that's where I'm marking things as being above or below the line. And down the bottom here, countries where boys scored better than girls on average in math. So Colombia, Germany, Singapore, and Canada. There are a lot more countries where boys score better than girls on math. But the key thing here is it's not universal. In some countries, that girls do better than boys on average. And we put so much emphasis on boosting girls at math. I don't see anything wrong with that. But the thing is, it's not universal. But on the other hand, let's look at reading. So the middle plot is the difference between the averages in boys and girls scores. And you'll see in every single country, and it's actually true in every single country across the globe, girls score better than boys at reading. Why don't we hear more about that? So that was one thing, looking at this data. I'm a mathematician, and I grew up being a talented math student all the way through school. But we still hear that girls need to do better at math. That is a message that we're saying to young girls as well. But I would flip it around. I say, actually, boys need to do better at reading. Okay, this is getting political, and I'm getting emotional because this is something I discovered by looking at this data a long time ago, but we still hear it again and again. We get stressed about girls not performing as well as boys. Well, they do. In some countries, they do. They outperform boys. So in Australia, actually, the 2015 scores, which is these ones, there was no gap. There was still a lot of media that stressed about girls not doing as well as boys. But so that's what the data tells us on standardized scores for 15-year-olds. Let's look at another one. This is another politically charged one. This is the 2016 presidential election in the USA. So not Australia, but in the USA, there's a lot of political polls. And so you can really get a good measure on how the candidates are appearing to fare, at least on the national, across the whole person-to-person popular vote. So the plot here is a timeline leading up to the 2016 election, running from April up to November. And then vertically, we have the percentage point difference between the two candidates in that year, Clinton and Trump. And each dot corresponds to a poll that was taken by different pollsters. Sorry, this should, this is supposed to be interactive and it was working a moment ago. I have to say, I also have been experimenting with slides today. Has anybody heard about the Quarto revolution? Okay, so this is my first time making Quarto slides instead of Sharingan slides. And there's a few little funny things that happened at the last minute, but as we mouse around, these should pop up and show which pollster actually ran the poll. The color indicates a different pollster, and there's generally a lot, but I've colored according to the 10 most common pollsters and then bunched everybody else into another color, which is gray. But so it's a messy plot in that sense because there are a lot of different pollsters operating. There's a lot of different colors. And so it's really hard to digest all those colors generally. But the main thing that I think you can notice is that some of these colors, it's coming up. It's just a little bit off the position of the cursor. So the labels are popping up. So if you look at the bottom of the line, there's some light blue points, and the light blue are almost always below the line, which means they're almost all predicting that Trump was going to win the election. On the above the line, the red dots are almost all, the bright red dots are almost all above the line. Right, so then there's a bit of a mix, but one thing that you learn when you look at pollsters, polling data in the US is that there is a difference in the average for each pollster. So some pollsters tend to produce results that are several points above for one candidate versus another pollster. And that's really important information in the sense of if you're listening to the news leading up to an election and the news reports, this poll had such and such a result. If you know who the pollster is and if you know the data, you'll know how to adjust that number to get a better estimate of what maybe the popular vote will be. So this was the first time I observed this was in the Obama, forget who he was against election, the first polls, that was a bit staggering because you kind of expect pollsters to be operating objectively. It's not true for the most part. There's a political agenda behind many pollsters. Another one for traveling, which you haven't done much. There's an amazing database from the Bureau of Transportation Statistics in the US, and you can look at every single commercial air flight since 1983, I think. and analyze air traffic across the states. And it's really fascinating. For one thing is the median departure time is negative, generally, if you're looking to basic statistics. So most flights, or at least more than 50%, leave just a fraction early. Be aware of that. This one is looking at different airports. So I've got arrival delays on the horizontal axis and a box plot corresponding to different airports. Some of them are marked here. That's Newark, San Francisco, LaGuardia, Chicago, JFK in New York City. And down the bottom here, this is DFW. On the right-hand side here is volume of flights. So the bigger the bar means that airport is handling a lot more traffic. The one interesting thing to point out here is that Dallas-Fort Worth handles a lot of traffic, but it does so more efficiently than most of the other airports, major airports. Now, this is all before the pandemic, so I'm not sure that's necessarily the case anymore, but it definitely helped me work out which airports to try to target to go through and which ones to avoid. Here's another one. So we are very concerned about climate change today, and CO2 is one of the big indicators of the atmosphere that has propensity to increase the temperature or related to increase in temperature. But this is CO2 measurements taken at a handful of recording stations across the globe. So horizontally here is year. It's only up to 2018, but I could have taken this up to like last week if I want to redo this plot. And the 4 different stations that so in the vertical axis here, I have CO2 in parts per million. And the plots are organized from north to south. So the top plot is up at the North Pole, basically, and the bottom, not quite, actually, out in Alaska, and the bottom one is at the South Pole. And one of the really interesting things is that CO2 has a seasonal effect, a strong seasonal effect in the Northern Hemisphere, and it doesn't have that so much in the Southern Hemisphere. The general pattern of CO2 is exactly the same. So if we overlaid these 3 curves, they are exactly the same up to that seasonality. It's a very pretty data set. It's very pretty and actually is real data. Generally, when you see pretty data like this, you think it's synthetic data, but it's not, it's the real data. So the interesting thing is that CO2 is seasonal in the Northern Hemisphere for whatever reason. And it's not in the South. Right, one last example, which was from a couple of years ago when we had those horrific bushfires before the pandemic. One really nice innovation in recent years is satellite data that's measuring hotspots across different parts, particularly all across Australia. And these are the hotspots in Victoria. And maybe this is less. This is actually where modeling helped a lot. It's not just the graphics, but the graphics makes it a little bit easier to see that. One of the concerns that we had at the time, or was in the media at the time, is that these fires have been started by arsonists. Again and again, you see in the news reports that the terrible bushfires we're facing was due to arsonists. But if you take the hotspot data and use some statistics to cluster it to get the ignition point of a bushfire, and then you combine it with a lot of other data like distance from campsite, distance from road, weather patterns, vegetation, and use that with historical data to predict the cause, you'll find that most of the fires that started in that 2019-2020 season, 82% were from lightning. So, and only 4% from arson. And the light blue here is the arson. And they're just the arson points are close to some of the major centers. So overwhelmingly, the data tells us that lightning was the cause of the bushfires. as opposed to others. Alrighty, so those are just some examples of things that graphics has played a huge role to help me understand things around me, including some of the work that I do in terms of high-dimensional data and complex machine learning models. I've learned a lot about how they perform just by making plots. So plots, the plug is, without making plots, I wouldn't have learned most of the things that I know about life. And plots help us to let the data share its secrets. It's just really an important exercise. So here's the next one. Just a simple plot. And there's 4 color groups. Hopefully you can see the 4 colors. So the question for you is, have we got separated clusters? And everybody's not going to answer because you know it's a trick question. So it really looks like it, right? That there are 3 quite separated groups and 2 that are a little bit not really separated, but a little bit distinct from each other. So it looks like it, but the problem is, yeah, it isn't actually. This is due to some more underlying pre-processing the data that has made this look like there's a pattern. But this is really how we often come to plotting data. You have a plot and you make some assessment and some decisions from that single plot. The problem is, looking at this one would be misled on the problem that was being solved. So it's really important to provide some tools to help you calibrate what you're taking away or making decisions from a plot. So I use apophenia in the title. I thought, oh, I better define it. And we all do things like this sometimes when we have fun, look at the clouds and try to point out different patterns and shapes and objects. And we do this all the time in data plots too. I'm not sure how many of you use residual plots when you're teaching basic statistics, but it's quite fun to see what students write about the patterns that they see in the residual plots. So that's actually called apophenia. There is a word for it. Someone else introduced me to this word, which is interesting. And it's a tendency we have to see patterns and connections when really there isn't. It's just random. It's just due to the sample that we have or the way that we've processed things. So let's look at this one then, right? So now I've got a set of 12 plots. Which plot exhibits the most separation between the groups? So it's a real question now. Six? Who thinks 6? Oh, that's pretty widespread. All right, yeah, it looks good. Right. The data plot is actually 12, and you probably wouldn't have recognized it because I did a switcheroo on you and changing the color scheme. But if we go back to the data plot, that's the original. I think it's 12. It's been squished a little bit as well. So it's the same problem context that we're working with. 12 is the data. All of the other plots were generated by taking the color label and just scrambling it. Reassign the color label to the rest of the data matrix, row of the data matrix. Everybody's looking at me as though you can't believe it. It's the context of the problem. So we're starting with a high dimensional data set. Actually, this time it's something like 40 variables and 48 observations. And we're doing linear discriminant analysis. Who's done linear discriminant analysis? Few people. Who's done principal components analysis? More people. Okay, So linear discriminant analysis is principal component analysis, taking groups into account, finding the best two-dimensional projection of the data where the groups are the most spread out rather than the data is the most varied. So in each of these plots, what we've done is to do linear discriminant analysis, find the two-dimensional projection where the 4 groups are the most separated. But we've gone from 40 dimensions down to 2, and we only had 48 observations. So what we can learn from this is that association between group and the rest of the observations is even worse than by chance. Right. So this has actually been a really useful exercise in helping talk my gene expression collaborators to about spurious findings of differences between gene expression when you're working with high dimensions. So in a sense, it's not necessarily this data plot, but the data plot was used to show, oh, there's a difference in these groups, but without taking into account that once you get to high dimensions, everything is really sparse. And so if you've only got a small number of observations and a lot of variables, any way you slice it, you can find separations. And so this is a way to help calibrate that exercise and show the enormity of space. Alrighty, so just reiterating, I still argue that we don't make enough use of plots in all of our work. And it's a really important exercise. It's a way of really making discoveries and not failing to find something. One of the tragedies, if we're really strict in our statistics, is failing to find something that's really obvious, and that's a tragedy. So it's really important for making discoveries, but it's also important to guard against false discovery. So with our new modern computational equipment, we can do that. So the strategy of inference with data plots follows very much along the same lines as you do with regular statistics. So if you haven't done statistics for a while and need a refresher, in a classical setting, you start off with a null hypothesis pair and a null hypothesis and alternative hypothesis. The means are equal as a null versus the means are not equal as the alternative. There's a lot of previous work that's gone into determining what the appropriate test statistic is, like the t statistic, and then what the distribution of that test statistic is, assuming that the null is true. And so we have these lovely calibration curves that if our observed statistic value is in the outer part of our sampling distribution, then that means it's very unlikely to occur if the null hypothesis was true, which means we don't believe the null hypothesis. Right? So if it's very unlikely to occur if the null hypothesis is true, then we say we don't believe it because it's too extreme. So that's the grounds in classical testing for rejecting the null hypothesis. All right, for visual inference, it runs very similar. Now, we don't tend to start off with a hypothesis, but I'll talk about this in a moment. The way you construct plots, you can consider plots to be a statistic. And the way that you construct the plot actually dictates the null hypothesis that you're testing. And on the basis of that, with a lineup framework like this, putting the data plot in the context of null plots, and then engaging an audience to pick the most different one, then we can put some statistical significance on it. So let's put some more structure to that. Right, so the inferential machinery is why is a plot a statistic? So how many people use ggplot for making their, okay, reasonable number. If you're using ggplot in R to make your plots, if you're using it effectively, you're taking advantage of the grammar. And the grammar is like this: you have some data, you pass it to ggplot, you use a geom, whether it's a bar chart or a point or a line, and you map the variables in your data set into elements of that geom. You might add some nice styling. So statistics are purely functions of our variables. And that's what the grammar gives us. So when we specify that we want V1 to be mapped to the x-axis and V2 to be mapped to the y-axis and CL to be mapped to the color, and we give it a point geom, that point geom is essentially the function of V1, V2, and CL. Right? So that creates a functional relationship between our variables. As statisticians, we think of variables and the representation in the plot. The second is what's the appropriate null hypothesis that plot specification is giving. So just generally, the null hypothesis, there's no pattern in the plot. Anything that we see is just from random sampling or spurious. And the alternative, there's some sort of pattern. But more specifically, depends on how we're doing that mapping. That we might get more specific than that. And on top of that, we need to have a mechanism for generating null data and null plots from that in which to calibrate the data plot. So let's specify one directly. So here, oh, sorry, I did jump over a few things here. So we need to set up a null generator, which is going to be some operation on the variables that we've measured. And we're going to generate a bunch of nulls and put the data plot in amongst those nulls. So that's the adaptation to ggplot to do that. So here's an example. This is using the empty cars data set. That's a common one in available in the tidyverse. It's using a permutation as the null generator. It's taking one variable and scrambling those values relative to the other variables. And the lineup is going to generate 12 plots. The plot specification, miles per gallon is mapped to X, horsepower is mapped to Y, and the variable that we're scrambling, cylinders, is mapped to color. And we're faceting by the sample ID because we've generated 11 null data sets and we've got our data as well. The rest of it's all just the nice styling. Okay, so we've got 12 plots here. Can you spot an odd one out? Plot 3? You picked the data plot. Alrighty, so how many people agree with that choice? Most people, because the red group's more consistently together and the light blue and then the dark blue, whereas all the rest, it's much more spread. So that's the exercise basically. And what this lineup function will do, we'll go through that in a moment, is also it encrypts the position of the data plot. So you can actually test yourself on this. And you could use this decrypt code to determine which position that's in. I think there's a couple of questions in the chat. Oh, good. We're getting some guesses from the chat. Perfect, from Zoom. Alrighty, so just reviewing. The way to add that inferential machinery, define your plot based on the tidy data. In tidy data, you have variables in your columns. So define your plot based on tidy data, add your data in, and then add the comparison in. So add your null generator in and add the lineup function. Right, so that's the adding the inference onto your existing workflow. And then once you've got a lineup, you can now show it to people who don't know anything about your data and ask them to pick the odd one out, right? Or you might be more specific if you have some particular type of problem in mind. And so then we can start calculating statistical significance and also the power of that particular plot design as well. So we talk about power of statistics. Same procedure happens with plots. If you design your plot in a different way, that plot might be more powerful for a problem than another one. Right? So the same analogy holds. So you can calculate the probability by, you've got K uninvolved observers, and by chance that any observer picks the data plot is one out of the number of plots in the lineup. And when with K observers, if you have X people that pick the data plot, then we can calculate a p-value. So the probability that X or more people selected the data plot is our p-value. You could think about that as like a binomial distribution. So if you've done binomials before, binomials are a little too simplistic. It gives slightly too low p-values. So we've got a couple of different ways of calculating that probability to take some dependencies into account. So we can calculate a p-value for visual testing with this function. I'll talk more about that function in a bit, but specify how many people detected the data plot out of how many people that were asked and how many plots were in the lineup. So if 2 people out of 23 pick the data plot from a lineup of 12, then the binomial formula would give a p-value of 0.58. But if we use a simulation approach to estimate that p-value, it would be 0.52. If that number jumped up to 5 instead of 2, then the p-value from a binomial would go under 0.05 and just a little bit over if we use a simulated approach. Takes dependencies. Once you get to 8 people, actually before you get to 8 people, but 8 people is highly significant. And then on the flip side, we can look at the signal strength, how many people pick the data plot over how many people were asked as a sense of power. That only makes sense if you really got one plot design and another plot design and you're trying to compare those two. Alrighty, so this is our package that will do these sorts of things for you. There's a lineup function which embeds your data in amongst some nulls. There's a selection of null methods, permutation, simulating from a distribution, calculating a linear model and the residuals from the linear model, and even the sum for time series modeling. P-visual calculates the p-values like I just showed you. And then there's a visual power function that just calculates that proportion. And there's also some interesting work on trying to get distance measures to measure how much a data plot should be detected from nulls that we can compare with human testing. Just one more thing. These seem like simple, but when you're actually working on a real test, you have to give people the option to pick more than one plot. And you also have to give people the option to pick no plots. It's different. So the calculations here will take that into account, adjust if people pick more than one plot. That's the website for the package. So we're going to run through an example now. I've got good timing now. And so just run through all of that with you. So we're almost ready to take your phones out. So this is the data set that I'm using for an example. It's tuberculosis data from the World Health Organization. It is current, but I've only got data up to 2012 because the way it was measured, incidence was measured, changed after 2012. And I'm a bit lazy. I just want to give you an example. So I'm only using up to 2012 data. So this is the data as you would see it from the World Health Organization. So question for you who are tidyverse users, is that data in tidy form? Someone's going to answer. Is the data in tidy form? Or someone's got to be brave enough to say something. Yep. No, yeah, I wouldn't be asking otherwise. Why isn't it in tidy form? You don't know. That's all right. Don't know. But so this is actually a pretty common way of delivering data, and you have to be pretty. Yeah, you have to be pretty cluey to decode it, I think. But some of them are easy, like country and ISO 2 and ISO 3 are pretty straightforward. If we go scroll down, these are the variables that I'm really interested in. New SP M04, new SP M514. Let's look at the end, M014, M1524. Scroll down a bit further, F04, F514, F014, F1524. Does that code look familiar to anybody? F and M usually mean gender or sex. Good, that's one. What about the numbers? Age, yeah, age category. Yeah, so the columns in here correspond to variable information. So the variables that we have or primarily interested in is the country, the year, and then sex, and age group. That's it. All righty, so we need to first get the data into that shape. Sorry? Yeah, so discard the outliers and NAs. Yeah, so we'll do that. So this is the raw data, and I haven't trimmed off the years, and you'll see that there are a lot of NAs in the early years. It's 1980, 1981, 1982, but glimpse is just showing the first few records. There is data there, not all missing. Okay, so the first thing is get it into tidy form. And so use your pivot longer and your separate function and your string split, and we can get those labels into variables. So now we have 6 columns in our tidy data. Country, I kept ISO 3 because sometimes it's nice to have the 3-letter code. Year, oh, I should have put count last. I should have reorganized the order of these, but sex and age are the other 2 variables. So we've got 5 variables: country, ISO 3, year, count, sex, and age. Sorry. This is a mistake. Count should not be considered a variable. Why? It's just an aggregation. So we've got aggregated data. So count is just the aggregation. The actual variables are country, ISO 3, year, sex, and age. And count is just a number in that category. Right, so we've got data in tidy form. Now you've got the data, you know what variables you're working with. What are the questions that we can answer with that data? I'm only going to focus on Australia, but the types of things that we would want to investigate are, is there an increasing or decreasing trend in tuberculosis incidence? Is there a difference by age? Is there a difference by sex? Is there a difference by age and sex? Is the trend different by age? Is the trend different by sex? Is the trend different by age and sex? That probably covers most of the things. It's not that complicated data. Alrighty, so suppose we want to investigate question 1. Is there an increasing or decreasing trend? What type of plot should we make? We always have lots of choices. What type of plot would you make? Time series? So we definitely want year. So we want year mapped to the x-axis. And then we might have a choice of what to put on the y-axis. Would you put a dot? Would you put a bar? So someone says a line graph online. Okay. I would tend to use a bar because it's counts, and that way you know that 0 is in your range. So I'm going to show you a bar chart later. Let's try question 6. Is the trend different by sex? What type of plot would you make for that? Sorry? Yeah, so you'd map sex to color. Yeah, so map sex to color. We still want trend, so want year on the x-axis. And so say we use a bar chart and we fill by sex. Would you use just the bar itself, or would you force it to be 100% chart instead? Sure, I can read that. I would fill the bars because you care about the proportion. If probably we haven't looked at the data, but probably we'll get a different count from one year to another, and so it's going to make it difficult to compare sex. So if I want to look at the trend by sex, I would forget about the magnitude of the count and focus on the proportion of the sexes, right? Oh, yeah. Simpson's paradox, we always have to worry about that. That's an important reason to sort of build up a whole bunch of plots so that you can get a handle on Simpson's paradox. Alrighty, so here's the tuberculosis data plot. We're making, we're grouping by year and then summing the counts that we have. So we're summing over the other categories. Putting year map to the X variable, Y is going to be mapped to count. And geomcol is just another way of doing a bar chart where it tells ggplot, you've already done the counting, so you don't need ggplot to counting. So for the question, is there an increasing or decreasing trend? What's the null hypothesis for that? No trend. Yeah, no trend. And what would be a possible null generator? Just scramble year. We might see that might be a little bit too simplistic, but let's do that for starters. We'll just scramble year, and that means that we're going to break the association with year. Alrighty. So I've done that. And now here's where you want your phone. Grab your phone. Let's see if we can see if I can see your responses too. We've got 12 plots here. Go to menti.com, and when you go there, type this code in. And you should have a choice of 1 to 12. So pick one. I think I've only allowed you to pick one. Oh, the question is, which one's different? I didn't give you choice, nothing. This is the first time I'm using Mentimeter because I'm hoping it works. Yeah, I want to keep it easy. And Mentimeter is not very sophisticated either. Everybody done? Oh, a few more time. we've overloaded it. Okay, maybe we've got enough. I'm going to just pop out of full screen to get to the Mentimeter, and hopefully, come on. Oh, beautiful. Alrighty, so this is a summary of results. Oh, just one couple more coming in. I should throw that data away because you can tell. Okay, so oh, there's another one coming in. Yeah. Okay, well, we're not going to be too formal. So I know which is the data plot, which is 10 actually. And now let's see, there's quite a few people that have picked 10. How many dots are there? Has anyone got it counting? Oh, perfect. 48. And 1, 2, 3, 4, 5, 6. Sorry, which one's 10? Oh, no. Okay. This is what crowdsourcing is for. Okay, so let's calculate the p-value for that. So I need to get out of my slides again. Oops. Sorry. And the next slide, I've got that p-visual calculation. So we had, how many was it? 13 out of 48? 8. And hopefully I've got my code. Well, I'll just rebuild my slides, render them again. They take about a minute to render. Okay. And it always goes, wait. Sorry. One thing I forgot to do was to eval equals true. I just take that off. Sorry, I've got to render again. Oh, I can just run it in my console. So it. Alrighty, it's a number there. Hopefully it's still rendering. That might be right now. Okay, voila, we've got a p-value. So 13 people out of 48 is a lot of people agreeing that it's different from the rest. And so the p-value will be really small, whichever way we calculate it. It's quite large. Now, true, exactly. And so one thing is that there's still a lot more work in effectively calculating or estimating p-values. And so there is a more sophisticated approach than what I'm using here, which puts a distribution on every plot and would take into account that if people put a lot of loading on another one, which is, yeah, it's important. So there's still plenty of work to do statistically on this. Alrighty, so just wrapping up. Good job, everyone. You picked many people picked that one, enough to point out that plot as being different from the rest. So just in summary, what we have at this stage is that we have equipped data plots with statistical inference machinery. With the grammar graphics, data plots can be statistics, and those data plots can be tested in an equivalent manner to formula hypothesis testing without pre-specifying that hypothesis, and using randomization techniques. One of the best ways to use this machinery is actually to test your plot design. We haven't done that today, but being able to know whether this is the best design to communicate something, this approach can help decide which is the winning design objectively. And then lastly, one thing that I've been working on for a few years, and we're not there yet, is to build computer vision models using this infrastructure. I think this infrastructure helps to do that, so that then you don't have to bother with your residual plots. You can upload them to some computer or robot and have it do the work for you. That's my goal for soon. So thanks for listening. And yeah, I really appreciate your interaction here. And in the slides, there's more reading if you're interested in that, and links to the resources too, if you, which is also down the bottom here, if you want to look at these later. So thank you.
Do you have any questions for Dianne?
Yeah.
Ask about this computer vision. So how much work from this happened?
So we've done quite a bit in terms of one, seeing whether so using the old experiment data that we have, we've got probably about 20 experiments with different sorts of problems. We have used the human subject results and used the null generating mechanism to generate a gazillion plots to train a computer vision model, and compared the how well that's done relative to people. So one thing is that we can say is that that model didn't do anywhere close to what humans did. And it seems surprising, but it's not surprising also, because if there's small variations, the computer vision model gets messed up too. But it still does, it still would handle probably 80% of the tasks, which is probably enough anyway. It doesn't have to do as well as what a person or crowdsourced people might do, but still our vision systems for this type of problem, or reading data plots, do better than the computer. And those experiments that I've done. What we're currently working on is doing a bunch more very focused human subject experiments purely for using residual plots. So purely a residual plot and all sorts of deviations for what you might see in a residual plot. So we're just building up that database right now, and then hopefully build a computer vision model that will do really well on those, and allow a service to upload your residual plot. Right. So, yep. Yep.
Dianne, thanks for the talk.
Thank you.
I have a more general question, and I want to start off by saying that me, plot, and maybe Matt over in the Python side has always been a very free form of agency to be able to bridge that gap between me and the data. And I would like to know if you feel how you feel about new tools coming out that are much more point and click based, like you would say Tableau or Power BI. Seem to be really popular, especially in the industry, maybe not so much in academia, one industry. And how do you feel about these tools coming out and maybe taking away this sort of agency of people with respect to their own?
Well, I mean, we've always had that. Say, I've been around a long time now, so every so often you get a new tool that basically is point and click GUI. They went away for a while with R and with ggplot, but Tableau's been around for quite a long time. So they've always been there. I don't use them. It drives me crazy if I don't have control. I'm not that big a control freak, but I do like to control my plots, and I do like to be able to specify them in the way ggplot. So I don't see that will ever replace what most data analysts do. It provides an easier entry point for many people. And I think Tableau provides sort of even some, you see some news agencies that will, or news sites that will use Tableau plots. Some government agencies use Tableau, but I also don't like the style of them too. So So, I mean, it's not a new situation, really. Point and click GUIs have been around for a long time. People are valuable. We'll never get away from people are really important for many things. And robots are not replacing people for most things. It's just those repetitive tasks that we don't want to do anyway. So, yeah, point and click is generally, I don't want to do that. Hopefully other people like me too. This question here.
The question you ask is important, right? So you ask the question, which one is the data? But I was really hearing which one's different.
Yeah, I'm asking which plot is different.
Yes.
Yeah, and always asking which plot is different.
But is there a range of questions you can ask with which you probe different things?
So one of the nice things about setting it up this way is that if you're just asking people which one's different, you allow the alternative to encompass every possible variation from no pattern, right? And so that's actually useful, and that's different from a lot of our classical hypothesizing where we test for ape-specific structure. We have an omnibus test for any departures from it. So most of my real work in using this is that general one. It's just ask which one's different. And you get to see mostly people picking up what you expect to be the data, if there's something different in the data. But it is interesting that people do cue on different things. So if there's like an outlier and you've got box plots, people often will pick one of the null plots that's got an outlier in it. So there are definitely ways that people will cue to different things in plots.
In your test, just one less person picked the plot number 12.
Yeah, we should look at that one again. So yeah, I did gloss over that. So yeah, a bunch of people almost the same picked 12. Who picked 12 and why did you pick it? Why did you pick?
More flattish than the others, like more
Oh,
and the others all looked like they had a division.
okay. Yeah, so you really didn't want to see a trend.
I couldn't see that in others, so I just picked the ones that went.
Yeah, they were more up and down in a sense. Yeah. Oh, that's interesting. Yeah. So if I want to do a validation against a formal test, I would do a very specific question. Because if I want to face off how this would work as compared to a t-test, I'll ask very specifically which one has a difference in the average. But mostly, yeah, you want to, so this is interesting, I think, to learn that you were looking for that flatness as being different from the rest. And that's good to know.
Yes,
Yeah.
but it's
Yeah.
like biasing.
Well, I would say the other way. It's actually it's helping us to know what other types of departures might be important. And now, if we looked at another sample of nulls, or we did a whole series of nulls and lots of different people, probably that would all be washed out. We've got a fairly small number of people and just a small set of comparisons. So generally, if you're using it in practice, you want to do a bunch of alternative lineups and have a lot more people evaluate those, and then you pull the results. And then I think it'll wash out then. I don't know. Yeah, no. We're pretty close to out of time, right?
Yeah, maybe now we'll give it time, and then like we do have 2 more questions. Maybe
Yeah.
I can come up and ask you.
Happy for that.
Would that be okay?
Yeah. Thank you.
Thank you, everyone, for coming. And we
Okay.
I'm a good friend with Rosemary Marklin. She's